Assalamualaikum. In this session, we will discuss in details about the NMR spectrum. NMR spectra generally appear as sharp peaks, and most of photons are observed between 0 to 10 ppm, and the chart is plot upfield to downfield. NMR peaks are measured relative to the position of a reference tetramethyl or TMS peak at 0 ppm on the chemical shift scale. This is how the NMR spectrum looks like, where TMS chemical shift always at the 0. The scale for the NMR spectrum is 0 on the right side, followed by the bigger number on the left side. This is the scale for chemical shift with the unit part per million. The peak always not appear as single peak, but appear as a splitting pattern. In NMR spectrum, the scale is quite different compared to other spectroscopy spectrum, whereas the scale is in reverse position with this 0 here, followed by the bigger number on the left side. The normal scale for the spectrum are 0 on the left side, followed by a bigger number on the right side. That's the difference between NMR spectrum with the other spectroscopy spectrum. The two important terms in the NMR spectrum are shielded and deshielded, upfield and downfield. This is the two terms that always use. What is upfield and shielded? Upfield is for the proton that are shielded. Means proton shielded is proton that attach to the saturated compound. And downfield is for deshielded, and the number are more bigger compared to the upfield. Is for proton that are deshielded are proton in the unsaturated compounds or near to the electronegative atom. What is the terms of chemical shift? Chemical shift is the chemical shift for a certain protons compared to the spectrometer frequency in megahertz. The symbol is delta and the unit is part per million when calculating by using this formula. This is the chemical shift for a certain solvent, and this chemical shift are fixed. Most of the solvent are in deuterated form, which is use the deuterium as isotope for the hydrogen when dissolve the NMR samples. Why deuterium had been chosen in the solvent? In this case, we want to avoid the signal of proton. That's why deuterium is isotope for the hydrogen had been used in the solvent. This is the fixed chemical shift for a certain protons, which is saturated followed by the unsaturated and the one that attached to the electronegative atom. We can see the trend when it become unsaturated, the chemical shift number become increased, and when attached to the electronegative atom also it become more bigger. This is the trend if we can see in the scale. So this is for the proton for saturated compound, followed by the unsaturated, and near to the electronegative atom. Since they represented in this way, what information that we can get from the NMR spectrum? We go for the next point, which is number of signal. Number of signal can be determined based on the environment of the proton, whether they are magnetically equivalent or not. See the example of toluene. In this case, how we can know the environment of proton is same or not? We see in this benzene ring, the proton are all in the same environment. So they have one signal for the benzene proton, and this proton are different signal which is on the saturated carbon. In this case, we have two signal with the 5 integration for 5 proton in the benzene ring. Goes for the chemical shift in the downfield. We see for the CH3 is saturated proton, and this one appear on the upfield of the chemical shift with the integration 3. Integration shows us the numbers of proton present in the molecule. Next example, we can see in this case, this molecule had a symmetrical molecule, and in this case, they have only appear one signal in proton NMR with the integration 6H. Next example, because of this methylene and methyl is a different environment, so they have two signal with different integration. Same goes to this example where I have 3 different chemical shift or 3 different signal, because they have 3 different environment of protons and with a different integration and position of chemical shift. Let's see the next example. In this case, this example is a symmetrical molecule and only one signal can be appeared. In this case, they have a different electronegative atom on the right and the left side, so they have 3 different signal. In this case also, they have 2 different environment. One is direct attached to the carbonate and one is direct attached to the oxygen, so they have 2 different signal. Next example is alcohol, also same, which is 2 different signal. When goes to the C double bond C, we have to understand that if symmetrical, so they have a same signal. If unsymmetrical with different functional group like this, they have 2 different signal. And if like this, one functional group, so they consider are not symmetrical anymore, they have 3 different signal. For the cycloalkane, in this case, without any functional group, they have a same environment, so they have only one signal. For chloropropane with one functional group, heteroatom, all the protons now become a different environment with 3 different signal. Let's see this example. In this case, how many? This one is one environment, 2, 3, and 4. The answer is 4. Next example, in this case, this is a symmetrical molecule. This environment and this one become same, and this one a different environment. The one in the middle is different. Total number of signal is 2. For this example, all environment are methyl group. All have the same environment, so only one signal. Next example is have one heteroatom. This have 2 signal, and this case, this bromine have one heteroatom of chlorine. Based on this heteroatom, all the protons now become a different environment in the benzene ring. Total is 5 different environment or 5 signal. This is 1, 2, 3, 4, and 5. example with the bromine heteroatom attached to these molecules. This molecule have 3 different signals, 1, 2, and 3. And this considered as symmetrical. So the methyl is 2 group in the same environment with the CH. This is 1 signal for methyl, and this CH is 1 different environment. Total signal is 2. In this case, all environment are different. Total number of signal is 1, 2, 3, 4, 5, 6. Let's test yourself by doing this exercise. Next part is spin splitting in proton NMR spectra. As I mentioned previous slide, the peak is not always appear as single peak. They always have a spin splitting. Means they will appear as doublet, triplet, a quartet, or multiplet. Based on splitting, rules are n plus 1. They always use n plus 1 rules. How to use these rules? Let's see this example. How we can determine the splitting pattern for each different type of protons. Let's see this environment, this methyl proton. How can I know the splitting pattern of this proton? I have to close this proton and see the neighboring proton on the left and right side. So both sides I have to see. On this side, is there any proton, neighboring proton for this CH3? No. So only on the right side, which is 2. By using n plus 1 rules, 2 plus 1 it becomes 3. The splitting pattern for this signal is triplet. Go for the next environment or next signal, CH2, methylene proton here. We have to see on the right and the left side how many neighboring proton. Total neighboring proton for this signal are 2 plus 3, it becomes 5. 5 plus 1 is 6. We can write down sextet or multiplet. If the signal is splitting into more than 5, we can simplify to put it in, write it as a multiplet. See this proton, how we can identify the splitting pattern for this signal. We have to see on the right and left side. On the right side, is there any proton? We cannot say that this one is a neighboring. It must be direct attached to the carbon. So the oxygen now cut off the neighboring splitting of this hydrogen. Based on this right and left side, the neighboring proton only 2. 2 plus 1. This one not considered a neighboring proton because they have oxygen here in the middle. 2 plus 1, it becomes 3. The splitting pattern for this proton is triplet. This example, we see, this example is a symmetrical molecule which is have 2 different environment, and how we can identify the splitting pattern for this signal. For this signal, we have to refer the neighboring proton on both sides. In this side, is there any neighboring proton? No. On the right side, they have 2. So use the rules n plus 1. 2 plus 1 become 3. The splitting pattern for this signal, CH3, is triplet. For this case, for CH2 methylene group, the splitting pattern is 3 plus 1. It becomes 4. So quartet for this signal. Position of the signal, chemical shift. Which one is appear in the upfield, which one appear in the downfield? Based on this chemical shift, this signal will appear in the upfield, in front of the scale of the NMR spectrum, and this one followed by this one, which is more downfield because of it direct attached to the C double bond O. We can see this in this way. This one is signal for CH2 and this one is signal for CH3, more upfield. It further away from the C double bond O. This one is more closer to the C double bond O. Splitting pattern is quartet here, because of the neighboring is 3, and this one is splitting pattern is triplet because the neighboring is 2. The integration for this signal is 6H because total 6, and this integration for this signal is 4H. Next example, the n+1 splitting pattern, how we can draw the peak of this splitting pattern after using the n+1. We have to follow the triangle tree. Means if the compounds have one neighboring proton, they have split into doublet. If have two neighboring proton, they will split into triplet. The peak have a different ratio, which is 1, 1 to 1, 1 to 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. If we can see how we can draw the peak. If singlet, we have to draw like this. Based on triangle tree, the doublet should be the same height because the ratio is 1 to 1. We refer to the triplet. We draw the splitting pattern. It's not in the same height. We have to follow the ratio 1 to 1. Same goes to quartet. All this drawing just based on the splitting triangle tree. As I mentioned just now, if the singlet proton, they have no neighboring proton, by using m plus rules, it becomes 1. The splitting is singlet. If one neighboring proton, it becomes 2, doublet, splitting pattern. If two neighboring proton, it becomes 2 plus 1 become 3. The signal become triplet. If 3 neighboring proton, 3 plus 1 it become 4. It become 3 of quartet splitting pattern. See this example. They have 3 different environment of proton, and how we can identify the position of the signal, which one appear in the upfield, which one will appear in downfield. In this case, we can see the most closest to the bromine atom is this methylene group, which is become more downfield, and followed by this signal, and last one will be the methyl signal. After we identify the position of the signal, we have to identify the splitting pattern of each signal. For in this case, by using m plus 1 rules, the splitting pattern for this signal become triplet because neighboring proton for this signal is only 2. 2 plus 1 become 3, so this one is triplet. And in the middle proton here, for methylene proton, the neighboring is 3 plus 2, it become 5 plus 1 is 6 step. The signal splitting pattern for this proton is 6 step. And the last one is the one near to the bromine atom. The splitting pattern only 2 plus 1 is 3. Why 3? Because we have to consider the neighboring proton on the right and left side only for the right and left side. We cannot consider more than one carbon neighboring. And this, hopefully you can understand, this one only consider this neighboring. If more than one carbon is not considered as neighbor for the splitting pattern. That's why in this methylene proton, the splitting pattern only as a triplet. In this case, neighboring is 5 because on the right side and the left side have a proton. It's not more than one carbon on the left or right side. This is the things appear as I mentioned just now. This one is for this signal, this is for this signal, and the last one is methyl group. The next example, in this case, which position of the signal for this CH? CH become more diluted and become downfield. This CH become downfield, and this CH2 is upfield because only near to the one bromine atom. The splitting pattern for this signal. You see the neighboring proton only one. Splitting pattern for this signal are 1 plus 2 is doublet, and splitting pattern for this signal, for CH signal, is 2 plus 1 triplet. You can see this one is a triplet signal here, and this one is doublet signal. Normally, hydrogen for the hydroxyl group not split neighboring hydrogen signal. They always appear as singlet with the integration 1 between 1 to 5.5 ppm. We have to try this exercise in understanding more about the splitting pattern. Let's see this example. How many neighboring proton for this signal? Only 2 neighboring proton. 2 plus 1 it becomes triplet for this signal splitting pattern. And in this case, only on the left side has a proton, on the right side they are cut off by the oxygen. This one is not considered as neighboring anymore. The signal become quadrate because 3 plus 1 become 4, so quadrate or quartet. You can write that as quartet. And this type of signal is cut off. Neighboring carbon is here. They have oxygen, they have no proton. The signal become a singlet because there are no neighboring proton. N plus 1, N is 0, no neighboring proton, plus 1 it becomes singlet. In this case, how many splitting pattern for this proton? We can see on the right side and the left side, 3 plus 3 become 6. 6 plus 1 is septet. We can see the signal is septet. In this case, this proton, how many? The neighboring proton is 2 plus 3, 5, 5 plus 1. By using n plus 1 rules, it becomes 6th. Correction here, it is 6th, not quadrant. See this example. Splitting pattern for this signal, CH3 is singlet. CH3 also singlet, only appear 2 singlet signal. Which one with more downfield? This one become more downfield because it direct attached to oxygen. This one more upfield because it only attached to the C double bond O. You can see this is the pink for this signal, and the green one is for the signal for this CH3. Next example, if cyclohexane, all the environment of the proton same, only one signal with 12 integration. Why 12? They have 2 here, 2 plus 2, 4, 6, 8, 10, 12 proton. That's why only single signal with 12 hydrogen integration. Same goes to this structure, which is symmetrical, means all the signal appear as a singlet with 12 integration also. 3 plus 3, 6 plus 3, 9, and plus 3 is 12. Benzene ring also have a same environment. If they are not attached to any heteroatom, all the signal considered as a same environment and the same position in the chemical shift, and with the integration 6H. Next example, they have 2 functional group in this position, CH3 and this CH3 position. Means this is symmetrical in this side. In this case, they have 2 signal. This environment is same for the methyl group, and all the protons in the benzene ring are same signal with the 4 integration, 1, 2, 3, 4. And this methyl become a 6 integration. If you can see, the signal here become in the upfield, and this signal become downfield because unsaturated signal. See this example, this is a symmetrical. All these methyl have the same environment, and they appear as singlet with the 9H integration. Next example, both have different environment. Which one will appear in front and which one is appear in the downfield. Here is appear in the upfield, and this one is appear in the more downfield because they direct attached to the bromine atom. You can see the splitting for this signal methyl 2 plus 1 is triplet for this signal, and this one 3 plus 1 it become quartet for this signal. B quartet and A is triplet. This one is upfield, this one is downfield. See this example also same, which is this C become more downfield followed by this signal, and last one the upfield one is methyl group. The splitting pattern must refer to the neighboring proton, which this signal neighboring proton is 2 plus 1 become triplet for this signal. A is triplet, we can see in front, and B they have a neighboring proton on the right and left side, which total up is 5 plus 1 is 6, so that's why it becomes 6 step. In this case, only I say if you want to consider the splitting pattern must refer to the right and left side only. On the right side there's no proton, on the left side is only 2. This one is not considered because it's more than 1 carbon. Only 1 carbon on the left and right side can be considered for contribution to the splitting pattern. In this case, 2 plus 1 become triplet. Next example here, this is the same environment for the methyl group. It become one signal, and this one CH3 methane group is a different signal, and this is more downfield because direct attached to the chlorine, and this one is come more upfield. The signal is how the splitting pattern of this signal. We see the neighboring proton is 1H, so N plus 1 become doublet for this signal, and this signal right and the left side total 6 proton plus 1 become 7, so they become 7 septet splitting pattern with the integration 1H. This one is integration 6H. We go for the next example. In this case, there are 4 different environments. This metal and this metal. How we can differentiate the position or chemical shift of these 2 protons, although there are methyl group. This methyl group and this methyl group, which one is more nearer to the bromine atom? If we can see through this structure, this is more near to the bromine atom. Thus, this proton will become more downfield compared to this proton. The upfield proton become A, the first signal appear, followed by the signal of B, we can see, and the methylene proton is C, and last one will be the methane. Methane will become more de-shielded because it direct attached to the bromine. For splitting pattern identification, we have to refer the neighboring proton for this signal. How it can be split? We have to refer here how many neighboring proton is 1. N plus 1 rules, 1 plus 1 become doublet for this signal. You can see B is doublet. D, if you can see the neighboring proton 2 plus 3 is 5, 5 plus 1 is 6. So it becomes 6 step for D. And C, we have to see on both sides, 3 plus 1 is 4. 4 plus 1 it become 5. So the signal become pentet for C. Correction here, this is pentet because 3 plus 1 is 4. 4 plus 1 is 5. 5 is pentet. Make the correction here. And the signal for A, the neighboring proton only 2 plus 1 become triplet. Here, example for ethanol, which signal will appear in front, the upfield, and which one will appear as a downfield. If we can see this hydroxyl group, this hydrogen from the hydroxyl group can be in between 1 to 5. It can be everywhere. Just based how we can identify this signal, they always appear as a singlet. Now we see this signal, this methyl signal. This methyl signal, where should be appear? it will appear in the arc field region because it's further away from the hydroxyl group. This one is more downfield because it's direct attached to the hydroxyl group. Based on the position of the signal, we know this one is here and followed by the hydroxyl group, and the last one is CH2. The splitting pattern for this one, 2 plus 1, this signal become triplet and this signal become quartet. So we can see in the spectrum, this triplet and this signal is C, it become quartet. And always singlet is the hydroxyl signal. In this example, if you can see how many signal appear, this signal hydrogen there is more downfield because it direct attached to C double bond C, and other signal is for these two methylene group, and these two is another signal. That's why we appear have a 3 different signal. In cyclohexane, this CH3 we can see is more arc field because it's not, this hydrogen is not direct attached as previous example. This attached to the carbon, so the chemical shift it become more arc field, 1.68 compared to H direct attached to the cyclohexane just now, 5 point something. In this case, for proton in the benzene ring, all fall in the downfield because in the benzene ring they reach of C double bond C, they are more d-shielded. In this case, if methyl group attached to the benzene ring, the position of the methyl normally it become around 0 to 1. Now it more shifted to the more d-shielded 2.32 because of attachment to the benzene ring. This C triple bond C considered as a bond string, so the H is more become a shielded because of the cloud of electron here. The H become a shielded proton. That's why it appear in the arc field of chemical shift. To simplify how the chemical shift difference when a different functional group attached to the C double bond C can be explained by this example. Now we can see this cyclohexane, the H is direct attached to C double bond C, that's why the chemical shift more further to the downfield. And this CH3, the H is not attached direct to the C double bond C, it attached to the C for saturated compound, that's why it become more arc field. This H is direct attached to the benzene ring, become more d-shielded, and this proton is attached to the C for saturated proton and considered as saturated proton. That's why the chemical shift is 2.32. This chemical shift is not fall in the normal region, which is 0 to 1 for methyl group because they are attachment to the benzene ring, and this C triple bond C is considered as saturated proton, which fall in the arc field region 2.9. The explanation details in this slide why the chemical shift for the protons attached to the benzene is more d-shielded, because the benzene ring effect itself can produce an external field and cause the aromatic hydrogen appear to the more high chemical shift value. They have own current ring inside, and the proton reinforced to the external magnetic field, and the aromatic hydrogen appear at high chemical shift value. On the other hand, the acetylene is in a shielding region. Acetylene is C triple bond C and therefore appear arc field. They are considered as shielding region. Aromatic protons on benzene are de-shielded and the protons on acetylene are shielded. Then that has cyclohexane, which was hydrogen attached to the carbon-carbon double bond. The de-shielding effect induced by ring current of benzene ring system extends beyond the hydrogen attach directly to the aromatic ring as shown in the chemical shift of methyl protons and on toluene, which appear downfield from those on the 1-methyl cyclohexene. The next example, for this structure, which one appear as a downfield, which one appear in the more upfield. This one will become more downfield, and this is the signal for CH2, and this is the methylene signal for next CH2, and the last one will be methyl. Let's try this exercise. How we can identify the number of signal for this example. In this case, how many numbers of signal is 2. This one is the same environment, and this one different environment. Total is 2. In this case, this proton have different environment with this one. Also 2 signal. This molecule, this proton, and here all are different. This molecule is a symmetrical molecule, only have 2 signal, because B and on the right side and the left side is same environment, and in the middle is the different environment. If you can see the mass spectrum here, only 2 signal, this one and this one. This the shown here is the zoom, the signal, that to see more clearer about the splitting pattern. Same goes to the signal, only 2 signal, 1, 2, and this one is the zoom part for this one, and this one is the zoom part for here. And this also same, 2 signal with different splitting pattern, and this is the zoom for splitting pattern here, and this is the zoom for splitting pattern for this split. How we can identify the splitting pattern? We have to refer the neighboring proton. For this signal, it become doublet. A, you can see doublet. For B, we can see 3 plus 3, 6, 6 plus 1 is 7. So total is septet. And this signal become doublet. A doublet. B become quartet, because the neighboring is 3 plus 1 is quartet. 1, 2, 3, 4. And this signal, here, this H2 become triplet, because the proton, neighboring proton only 2 plus 1 is triplet. Both sides same, and with the integration 6 for B, triplet. And A, we have to see on the right and the left side, total 4 plus 1 is 5, so total signal is pentet. See this example, how many signal? 1, 2, 3. The one near to the nitrogen dioxide atom will be more downfield, CH2. The signal is more downfield, followed by this signal B and A, the position. Now, determine the splitting pattern. For the signal CH2, the neighboring proton is 2, 2 plus 1 become triplet for C. You can see. B, we have to see the right and the left side. Total number of proton, 2 plus 3 is 5, 5 plus 1 is 6. B become sextet. This is signal for B. And A, neighboring proton only 2 plus 1, it become triplet. A, we can see the signal is triplet here. So that's all for the proton NMR spectrum, which I can summarize. What we learned today is number of signal and also spin splitting pattern. That's all for these sessions. Thank you.